Here we are, section 3.5, covering integration by parts. Now, integration by parts is a little on the challenging side, only because recognizing when to use it. Now, what you'll notice if you kind of thumb through the set problems here, these problems might as well, they could look like substitution as well. So the trick to what makes integrals difficult is being able to be okay with just trying something, trying the problem, trying using a technique, and if it's not working out, try the other one. So maybe try substitution, and if it's not working, okay, let's try integration by parts. So integration by parts is a formula, and what it's saying is we're going to look at some problem and break it up into something where we're going to say we have some function u and some function dv. So meaning, and then so what I'm saying when I say that is we're going to break it up into something that we're going to just call u, and then another piece where we're going to say this is dv. Okay, so you're just breaking your problem up into kind of two parts. And then the reason we're doing that, one of the parts we're going to take the derivative of, and then the other part we're going to take the integral of. Okay, so one way to look at this is by saying, well, do I know how to do the derivative, or even better yet, do I know how to do the integral? If I don't know how to do the integral, then I'll do the derivative of it. So this is one of those things where I think it's better to just watch it be done one time and see if you can get the feel of it. And then I'll show you how we fill in the formula and how we use it. So, okay, and again, it comes with experience. It comes with practicing and playing, and you start to develop some techniques. So what I'm going to do for this first problem is I'm going to call this part u and this part dv. So what that means is I'm going to say this first part that I said is u, I'm going to say let x equal u. Okay? And then for the other part, I'm going to say let e to the x dx equal dv. E to the x dx. Now, what I'm going to do is, of the thing that I let be u, I'm going to take the derivative of it. So the derivative of u is u prime, and the derivative of x would be 1 dx. Or if you wanted to, you could use the du notation instead of the prime. Whatever you like. I'm going to go with the prime since that's how I wrote it up there. Now, on the other side, we're going to integrate. Actually, you know what? I lied. I'm not going to use the prime. I'm going to use du. There we go. Okay, so then on the other side, we're going to integrate. The blue side, the side that we let be u, derive. Side that you let have the dx, side that you let be dv, integrate. So the integral of dv would just be v. Whoops, I wanted that in red. And then the integral of e to the x, well, that's good news. That's one of our easy rules. That's e to the x. And we're not going to worry about the plus c for now, but if you really wanted to, it wouldn't make anything right or wrong. We'll just tack the plus c on at the very end. So now, what this formula says, what you'll notice here is I have a u, du, dv, and v prime. So what the formula is saying now is this function, this integral, is equal to u times v, which we have right here. Here is u and v. So we just take those things and say it's x e to the x uv minus the integral of. Now I need v. Oh, that was e to the x times du. Well, so du is right there. And du is the same thing as 1 dx. So what we're doing is just substituting in all the little pieces. We're substituting in everywhere we needed a u and a v, we used a u and a v. So here we need another v, and here we need du. And you'll notice what happened. We still have an integral. But the good news is, now that we've done this method, we've used this formula, look what we're left with. Look what we're left with. Just the integral of e to the x dx, that original x that was on the inside is now gone. So therefore, I can do the integral of e to the x pretty simply. Integral of e to the x is e to the x, and then plus c. And remember, this would all be multiplying, or be multiplied by that -1. That -1 would distribute, or it'd be subtracting, however you want to look at it. So this would be x e to the x minus e to the x. And as we talked about in substitution technique, this c is just a constant, so it absorbs the pluses and the minuses. But if you wanted to, it would not be wrong to put a minus c there. But the book won't. It'll just put a plus c. So there we go. And of course, we could check this by taking the derivative of it. If you took the derivative of it, it would give you back x times e to the x. So that's kind of the fun part of this. That's kind of the beautiful part of this. There is no way on earth you would have ever seen, just by looking at this, that your answer would have been, x e to the x minus e to the x plus c. But after working it out this way, we can do it. So let's go back now and say, because I said sometimes it's easier to see one and then go back and look at the formula and understand what's going on. So what is the formula telling us to do? Take our function, break it up. We're going to call something u, and that thing u, we're going to take the derivative of it. Then we're going to say there's another part of it that we're going to say dv, or really what we're saying is we're going to do the integral of it. So you do the derivative of one piece, you do the integral of the other piece, and the only real rule here is that you have to use the entire function. You can't leave something out. Okay, so you have to not function, all the integral, the input of the integral. You have to use all of it. So then you fill into the formula. The integral of this is equal to u times v. So you just take your u and your v, and the way I write it, it's the diagonal. There's some other ways of doing it too, but this is the way I do it. It's the diagonal. So x times e to the x. Boop, there we go. That's what I did in yellow. And then minus sign is built in, right? Minus sign is built in, so minus the integral of, and now you're working your way along the bottom, e to the x times dx. And then you're just asking yourself, hopefully, can I do this integral? Now has this integral become something easier to do? And you'll start to notice some patterns as you do enough of these and as you play around with trial and error. But the one key point I'll point out with this, the reason I looked at this and knew what to do, is I said, well, one technique is if I have x to this, if I have x to a power, and I do the derivative of that, if it had an exponent of 1, when I take the derivative, it becomes an exponent of 0. So therefore, my du is really nice. There's no variables left. And if it was x squared instead, well, then it would be the same idea, except the derivative would be 2x, and I have a power of 1, and I still might have to do some more integration, but at least it would get easier, because going from x squared would become x to the first. So there's some little tips, there's some little tricks you'll start to notice, patterns you'll start to notice as you do more of them. Okay, so let's try this one. If you feel like you're ready, pause the video, give it a try. Otherwise, I would understand if you want to watch one more, because these things are a little different. Okay, so here we go. We need to break this up. We need to separate it into something we're going to take the derivative of, something we're going to take the integral of. So we can try that same pattern we used last time. Let's try letting u be the x, and let's try letting 2 to the x dx be our dv. Okay, so now I'm going to do the u is equal to x, and 2 to the x dx is my dv. Whoops, let me write it the other way. There we are. Okay, so now we're going to integrate this side, and we're going to derive the other. So the derivative of u is du, derivative of x is 1 dx. Perfect. Okay, easy enough. And then for the other side, the integral of dv, well, that's just v. And then the integral of 2 to the x, well, that's the exponential function, so therefore that's the same thing. That's the rule we already know. It's the integral of that would be 2 to the x divided by the natural log of 2, because it's just the rule, the integral, or the exponential function rule backwards, right? Okay, so there we go. Not too bad. So now what we know here is the rule. It's the diagonal. It's this thing would be equal to uv minus the integral of v du across the bottom. So my diagonal would be x times 2 to the x divided by the natural log of 2 minus the integral of, okay, now we have 2 to the x divided by the natural log of 2 dx. All right, so now let's ask ourselves, did this get any better? Now, the nice thing is this outside stuff, whoops, that's not what I wanted to do. This outside stuff here, we don't care how messy it gets because we don't have to integrate it. The integral symbol's gone. So when I say is did it get easier, what we're really focusing on is just in here. Did this integral now become something we can do? And a tip that I've found that sometimes helps students is whenever this natural log of 2 kind of freaks you out, especially when it's an integral, but remember, it's just a number. So a lot of students like to rewrite it with the constant on the outside, just like that, because the integral of 2 to the x times the constant is the same thing as the constant times the integral of 2 to the x dx. So this way, this integral to a lot of students looks way less scary than the blue line up above. So the integral now, let's see what we get here. The outside stuff just comes along for the ride. Minus 1 over the natural log of 2. And the good news, do we know this integral? What's the integral of 2 to the x? Well, we already did that. It's 2 to the x divided by the natural log of 2 plus c. And there we go. There's our answer. And if you wanted to, you could always combine like terms and do some fun stuff. But my test, I will not be grading you for these things to be simplified. I'm just grading that they are correct. And I believe Math AS will accept it also. Excuse me. But what we could do is we could distribute this through. So it'd be 2 to the x divided by natural log of 2 times natural log of 2 would be natural log of 2 squared plus c. And don't forget, this really distributes, but the constant just absorbs the negative. Okay, so there we go. And of course, if you wanted to, you could take the derivative to verify, which is good practice for your final exam, by the way. Just if you want to practice, these are good derivatives. We need to remember those because the final exam is cumulative. Okay, so that was problem number 2. So now let's hop on over to problem number 3. All right, now here's a little tip on this one. If we let u be x, well, actually, rephrase. Let me go the other way. If I let u be natural log of x and I let dv be x cubed dx, let's take a quick look at what that would look like. U equals the natural log of x. Okay, I know how to do the derivative of that. Okay, and x cubed dx, if that was dv, that looks good. I can integrate a power rule. This looks good. All right. A big tip, a tip-off that some people try to do, and what makes it hard for them is if they don't do it that way. If they try to go the other way, they try to say let x cubed be u. All right, which sounds good, and then natural log of x dx be dv. If we did it that way, what would that mean? We're going to come back to this. We'll come back to this. If I let u equal x cubed and I let natural log of x I keep doing that, dv equals natural log of x dx. What's the issue? All right, the derivative of this, easy, super easy. We got that. U prime or du is equal to 3x squared. That's no issue. Awesome. What's our problem? 3x squared dx. What's our problem? Well, what's the integral of natural log? Remember, the answer has to be natural log. So what's the question? I don't know any nice rule to that. So what we can do in just a minute, I'll derive that rule for you if you want to memorize that thing. But I don't know. I don't know what this integral will be. If you think you've got it, try to write it down and see, and then take the derivative of it and see if it gives you back natural log. But the rule for that one is tough. Okay, so sometimes an easy way to figure out how you want to break this up is by saying, if I try to, I don't know the integral of this. If I try to integrate it, I'd be stuck. So I'm not going to. I'm going to take the derivative of natural log, because I know how, and I'll take the integral of x cubed dx, because I know how. So the derivative of natural log would be 1 over x dx. That's not too bad. And the integral of dv would be v, and the integral of x cubed, well, hey, that's just x to the 4th divided by 4. So therefore, my diagonal would just be, I'll write the x to the 4th divided by 4 first. So it's just u times v. And remember, it's just multiplication. So a commutative property holds. You could write it however you want, and as far as order goes. All right, so it's my u times v minus the integral of the bottom row. So this would be what? X to the 4th divided by 4 times 1 over x dx. And you might be saying, wow, that got ugly. Well, stop and look at it really fast. X to the fourth divided by x, that simplifies down to be x cubed. And the constant 1/4 I can pull out to the front, can't I? So what I'm going to do here is make this 1/4 x cubed dx. And you'll see, so I just multiplied straight through. So that gives me 1 times x cubed is x cubed. And then I was divided by 4, so I pulled that out of the integral. And now this doesn't look so bad, does it? We can just simply say, all right, this chunk on the outside just comes along for the ride, minus 1/4. The integral of x cubed would be x to the fourth divided by 4 plus c. So therefore, x to the fourth times the natural log of x divided by 4 minus x to the fourth over 16 plus c. There we go. Not too bad, not too bad. So the power of by parts is pretty cool. It's pretty neat. It lets us integrate some things that there is no way we'd ever be able to come up with just using our rules backwards. But it also lets us do some things where substitution would just fail. So you would say, what would I substitute? Let what u equal natural log? Well, I don't have a 1 over x to work with. So this just works out pretty nicely. All right. So here's the rule for natural log. You'd say, all right, if I just had to integrate it, I'm stuck. I don't know how to integrate it. So what can we do? Well, if you think about it, it really is a 1. Let me see if I can get that bigger. There really is a 1 multiplying out here in front of it, isn't there? So what I'll do is say, I don't know how to integrate natural log. So I'm going to take the derivative of it. And I'm going to integrate the other part. I'm going to integrate 1 dx. So therefore, I'm just going to let u equal natural log of x. And I'm going to let 1 dv. I'm going to let 1 dx equal dv. So therefore, I'm going to integrate that and take the derivative of the other part. So here, the derivative of natural log is 1 over x. The integral of this would just be v, which is equal to, now, what's the integral of 1 dx? Well, if 1 is the answer, then the question was x, because the derivative of x is 1. And here we go. This is equal to my diagonal, which is x ln of x minus the integral of, across the bottom now, x times 1 over x. Oh, I forgot my dx right there. 1 over x dx. And what does that do for me? What does that do for me here? Well, that's kind of amazing, because this x and this x divide, so that just leaves me with the integral of 1 dx. And we just did that integral, didn't we? So that's x times the natural log of x minus the integral of this. Well, that's just x plus c. So the very interesting part of this that you may not have seen before, or you may never have seen this rule before, but the integral of natural log is x times the natural log of x minus x. Or it could be looked at as the derivative of this, the answer is natural log. Yeah, we've never seen that. So the idea here is a lot of the rules we have in the past actually can come from integrating this. And this method of letting your integral just be 1 dx and the derivative be the thing that you don't know the integral of. And you can come up with all sorts of fun rules. But the bigger idea here is you can, instead of memorizing a whole bunch of rules, you can just figure them out if you need to on the fly, as long as you know by parts. All right, so there were 4 practice problems, 4 problems to kind of run through, and the homework is just going to be problem after problem after problem of these, just more and more and more and more. Now, I will point out there is one type of challenge problem that does pop up in this homework, and it looks like this. Now, this problem is challenging because, all right, I don't see a great substitution. I don't see, and I will point out, I guess I will say, some of the problems will be mixed. Some of them should be done using substitution. Some of them should be done using integration by parts. And you're just going to have to try a method and see if it works. And if it doesn't work, try the other one. But that being said, most of the homework in this section is by parts, so you get a lot of practice with it. Now, this problem. This is one where we say, I don't know what to do. Okay, do we see a good u substitution? Well, I don't see much. I mean, I could let the denominator equal u, because that might be a good way to go. So then the derivative of that would be what, 4 dx, and I can kind of work with that, but I don't have any x's here to substitute out that 7x, so I'm kind of, it's a little sticky. By parts, yeah, I really don't see any by parts. What would I do here? Let u equal 7x and let dv equal 1 over 4x plus 9. Yeah, this doesn't look like a lot of fun. I'm sure we could try it, but what I'm going to do is show you another option that we have for substitution that we haven't seen before. Okay, and that's why I say this one's a little different. Okay, so if you're looking at this and saying, you know, the du is great. What I could do for the du is just divide by 4. So I get du over 4 equals dx. So that way I have a nice substitution here. Dx is equal to du over 4. That's easy enough. But the problem here is, and then this denominator here would just be u, right? So that's not too bad. And then over here we'd have du over 4. So that's not too bad. And then 7 times. Now the problem is I have an x, and I don't have any rule for x. Well, can I come up with one by using this line here? Now remember what I said. You can manipulate these equations as far as the constants. You just don't want to mix the x's and the u's. Well, so couldn't I just simply solve this? Subtract the 9, so give me u minus 9 equals 4x, and then divide by 4, divide by 4, divide by 4. So now I would have u fourths minus 9 fourths equals x. So that way now, everywhere I have an x, I can replace it with this wonderful equation, can't I? So that's exactly what I'm going to do. That's exactly what I'm going to do. I'm going to go ahead and give myself a tiny bit more room. Just going to scoot this over here. Delete that. Okay, so what I'll do is fill in here. It's u over 4 minus 9 over 4. There we go. So now I actually have something I can work with here, sort of. Let's clean up a little bit and see what we can do. What can we do to kind of simplify this a bit? I could pull this 1/4 out, so that would give me 1/4 on the outside, and I can pull the 7 out as well, can't I? So that would give me 7/4 on the outside. I'll use my eraser. Integral. Okay, so now on the inside I would be left with what? U fourths minus 9 fourths all over u du. And using a little bit of algebra, just a little bit of algebra trickery, or if you want to, you could look at it like this. This is u fourths minus 9 fourths divided by u over 1. And how do we multiply fractions? Well, we flip and multiply, so that'd be u fourths minus 9 fourths times 1 over u. And multiplication, we would just be distributing through. So that would give me what? U over 4u minus 9 over 4u du. And we can simplify now. U divided by u leaves us with a 1. So what do we have now? We have 7/4 times the integral of 1/4 minus 9/4 over u, or 9 over 4u, there we go, du. So now, is this something we can integrate? Well, this first term's just a constant, so that's not too bad, right? The integral of 1/4 is, well, who cares? The variable is x to the 0, so the power rule says add 1 to it. So it's just going to be 1/4 x to the first divided by 1. So hey, that's not too bad, right? Minus, now here I've got 9/4, kind of 9/4 times 1 over u, and the integral of 1 over u. Oh, that's just natural log. Not too bad. Natural log of u. Oh, and then of course don't forget plus c. Okay, so hey, that integral wasn't too shabby. So now what are we going to do? I apologize, this wasn't an x. That's supposed to be a u to the 0, which becomes a u to the first because we're integrating by u, not x. Okay, so now we have to go back and say, I can't have u's. I didn't start with u's, so I got to go back and substitute in. And we have to remember our formula for u's, not our formula for x's. No, no, no. We want our formula for u's over here. That's what we're going to substitute in. So everywhere I have a u, I'm going to replace it with 4x plus 9. So this will be 7/4 times 1/4. And I already forgot what I said. 4x plus 9. So 4x plus 9. And what I can do if I multiply across, this would just be, there we go, over 4. A little neater. So then minus 9/4 times the natural log of 4x plus 9 plus c. And for me, that is good enough. But if you really wanted to, you could distribute the 7/4 through or do something if you want. But there you go. So I wanted to show you that one. It's a little different. So sometimes if you're stuck, if you're just totally stuck, you're looking at it, you're saying, I'm not seeing a good u, I'm not seeing a good by parts, stop and ask yourself, could you use this version of the u sub where we use our u equals formula to come up with an x equals formula? And does that allow you to be able to do substitution? And the trick for that, the most common time we like to do this is when we're letting our u equal the entire denominator. Because then we get the mess up in the numerator, but the denominator is dividing by a single u. So when I break it up into fractions, we get simplification like we did there. And it makes it easier to do. Okay, so by parts, substitution, we just got to practice, 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 practice. What I will say is there's also one other type of integral that you're gonna come across here, and it's called tables of integrals. Now, the tables of integrals could be literally hundreds of tables, and it's just the idea of you open up a book, you look up a table, and you say, oh, that's what I have in my problem. It looks like this, so I'm going to use this formula. So in our book, we're going to only do we're going to use two different integrals, where these ones are ones that we're not going to be able to do by hand. We have no way of doing these. So what we're going to do is just say, if I see something that I can make look like the yellow one, then I've got my formula I'm going to fill in right here. Or I've got the blue one. Now notice the main difference for these two. One of them is x squared minus a squared all in the denominator. The other one is the square root of x squared plus a squared. So one's got a minus, one's got a plus, and one has the square root. The plus has the square root. And for those of you who know trig, if you ever took anything with trig, these are actually really easier to do using trigonometry. But since we don't know trig, we have to avoid it. So here we go. Is there some way I can make this look like the yellow? Well, first of all, that 4, that's just a constant. I can factor that out. I can just pull that out of my integral, right? So that gives me 1 over x squared minus, and I've got my dx out here. So now the only trick here is I need a squared. I need it to be some number squared. How can I rewrite 25 so it's some number squared? Ah, very good. And if you want to, you could think about it, but that's 5, right? So now I've got my formula. So what this tells me here is this integral here that I've got in yellow looks identical to this one up here. So I'm just going to fill in with my numbers. And the formula tells me it's 1 over 2 times a. 2 times a. Well, a is, for me, it's 5. So it's 2 times 5. We could write that as 10, yes, but I'm going to leave it like a 5 just to help people see it. Times the natural log of x minus a. And again, our a is 5 divided by x plus a. And voila, there's our integral. Oh, plus c. There we go. We did it. So on your test, there is no reason I expect you to memorize these. That's literally why we call them tables of integrals, is because you're supposed to look them up in tables. You're not supposed to memorize them. So these two will be provided for you on your test. They'll be in the directions, or they'll be included in the problem where they're needed. But they'll be there, so you do not have to memorize these. They'll be written out just like this. So just you may want to write them down for yourself just as you're going through your homework, so you can help identify them and come up with them. But on your test. You can't bring in notes or anything. So therefore, just be expecting to look for these and they'll be there. Okay? So this problem. How are we going to do this problem? Well, this one's going to make you want to drink a lot of chocolate milk because because this looks close. It looks close, but notice we need x squared, and here we have x to the 8th. Well, let's think. And here I have an x cubed in the numerator, and here I've got 5. This is going to take some major manipulation. So let's think about what we can do to make this fit. Now, I can't just take an x out, right? That only works with constants. So this x cubed's got to stay. Now, down here, I need to write this as something squared. So how would I write that? X to the 4th. Because remember, rules of exponents are if we have a power to a power, then they multiply, right? So 4 squared is 8. So there we go. I rewrote that as something squared. So now plus. Now I need to rewrite 5 as something squared, but it can't change. So what would I need to put on the inside to make it so that I didn't actually change my number? Because right now 5 squared is 25, not 5. Well, think about inverse operators. If I square something, then to undo that, I need to square root it. So therefore, the square root of 5 squared is 5. Okay, so now we're closer. But the problem, and then dx. But the problem is this doesn't fit our thing exactly. It can't have an x cubed in the numerator. It has to have a 1. Well, what if we do a little bit of u sub here? What if we have a little bit of u sub? What if I let u equal x to the 4th? Well, because then the derivative of that would be what? Du is equal to 4x cubed dx. Can I work with this a little bit? Let's see. Divide by the 4. So I have du over 4 equals x cubed dx. So now what? Everywhere I have an x cubed dx, I got that. I can replace that with du divided by 4. All right. I can work with that. So here we go. So I'm going to be left with du divided by 4. Nothing left in my numerator. Down here in my denominator, x to the 4th is the same thing as u. So I've got u squared plus the square root of 5 squared. Let me scoot that over a tiny bit. Du divided by 4. And there we go. Now, how did I decide to use u substitution? Well, I kind of used the same logic that we used way back when we started u substitution, which was look for something, a piece, where if I take the derivative of it, I'll get the derivative of it is buried in my problem. And that's what I saw right there. I said, look, I've got x to the 4th. The derivative of that is x cubed, and that's what was causing my problem in the numerator. So this is a good place to use u sub. So now you can see this actually does fit our rule, doesn't it? Try to get them both on the screen at the same time. 1 over the square root of something squared plus a number squared. That's what I've got. So now we can fill into our rules. I feel like, yep. Now if you want to, you can take this 4th out to the outside. That's what I'll do here. So it's 1/4 times the integral of, and what is the rule it's going to tell me? Oh, sorry, not times the integral. Times the answer. We know the answer. It's natural log of. Now we don't have x's. What do we have? We don't. So our variable is u's now. So instead of x, we're going to write u plus the square root of u squared plus a squared, and a for us is the square root of 5 squared plus c. So now just a little bit of substitution in here, and all goes well. Now, and if you want to, and a little bit of simplification, remember our u is really x to the 4th. So everywhere, as I'm going through here, everywhere I fill in a u, I'm just going to replace that with x to the 4th plus the square root of x to the 4th squared plus the square root of 5 squared is just 5 plus c. And you can leave it like that, or if you want to return things back to kind of how they looked originally, this would be x to the 4th plus the square root of x to the 8th plus 5, close my absolute values for natural log, plus c. Okay, whoops, there we go. And there is our answer. So the wonderful news about tables of integrals is things aren't literally just going to match up. Sometimes you have to force them to fit, or you have to look for a creative way of rewriting them to make them fit. So those were just two examples. Okay, but the main focus is there's usually very few table of integral problems on your test, one or two. The main focus on your test is going to be these problems up above, the by parts. So make sure you have this pattern down, the skills down, and just practice, practice, practice. Best of luck.